My name is Michael Barker, and I am a professor of civil and architectural engineering at the University of Wyoming. I am also the director of education with the Short Span Steel Bridge Alliance. Today, we will take an overview look at accelerated bridge construction applications that bridge engineers and owners can consider for their bridge replacement needs. We know that bridge designers, fabricators, erectors, and contractors have always been innovative in delivering bridge projects for owners. In this webinar, we will introduce some innovations that use modular designs for foundation and superstructure systems, and innovative design, planning, construction, and material selection for building bridges with accelerated bridge construction. Accelerated bridge construction, or ABC, has become an important part of the bridge industry in that it reduces on-site construction time and disruption to the public, and it improves project delivery time and work zone safety. In this webinar, we will look at accelerated construction bridge products, innovative ABC bridge systems, and advanced ABC construction techniques that has changed the way bridges are built to meet the owners and the public's needs. Some of the case studies we will look at and some of the videos we will see will seem like marketing for particular bridge manufacturing or fabrication firms as we mention their names and their products. And admittedly so, it is probably marketing. And if they get business because of this, well, that's good for them. However, we will consider that these are case studies that are options for the owner or the engineer when considering how accelerated bridge construction can meet their bridge needs. From the Federal Highway Administration ABC website, approximately 1/4 of the nation's 600,000 bridges require rehabilitation, repair, or total replacement. However, the work that occurs from on-site construction activities can have significant social impacts to mobility and safety. In many cases, the direct and indirect costs of traffic detours that result from a loss of a bridge during construction can exceed the actual cost of the structure itself. For example, full lane closures in large urban centers or on highways with heavy traffic volumes can have a significant economic impact on commercial and industrial activities in the region. Partial lane closures and other bridge activities that occur alongside adjacent lanes can also lead to safety issues. Because of the potential economic and safety impacts, minimizing traffic disruptions is a goal that should be elevated to a higher priority when planning bridge-related construction projects. Accelerated bridge construction is bridge construction that uses innovative planning, design, materials, and construction methods in a safe and cost-effective manner to reduce the on-site construction time that occurs when building new bridges or replacing and rehabilitating existing bridges. Now for the applications in ABC. We will look at examples that lend themselves to accelerated bridge construction by starting at the substructure and moving up to the superstructure. In precast concrete construction, the substructure is fabricated at an off-site precasting plant and shipped to the site. This shortens the on-site labor and construction time. With the high level of quality control attainable in a precast plant, high-performance concrete can be used. This results in more durable substructure units with higher quality and better finish. The higher strength of high-performance concrete also allows the use of hollow sections, resulting in material savings, lower hauling and erection weights, and decreased foundation costs. The use of post-tensioning with precast substructures will further improve durability by eliminating cracking under service loads and providing stiffer vertical elements that minimize deflections. Bridge pier columns can be prefabricated, brought to the site, and connected to the footing. Precast concrete bent cap beams are the most common prefabricated elements in bridge substructures. Bent caps are generally the most difficult elements to construct on site using cast-in-place concrete, where the shoring and the forming can be extensive. These have the benefits of the element being prefabricated off-site and only needing to be transported and installed on the site. Prefabricated substructure elements can greatly decrease the time of construction. Standard abutment construction can be a long process. Therefore, prefabrication can provide an excellent opportunity to reduce the overall construction time of a bridge project. Advantages of precast concrete integral abutments are that they eliminate the bridge deck joints, which is a common area for water leakage and deterioration in bridges. It allows thermal movements and girder rotations at the support. The soil forces are transferred into the bridge superstructure, reducing the size for spread footings or multiple rows of piles, and they are quicker to construct than traditional abutments. Sheet pile wall abutments are constructed from hot-rolled structural shapes with interlocks on the flange tips. These interlocks permit individual sections to be connected to form a continuous steel wall. Hot-rolled steel sheet piles have several advantages when used in the design and construction of bridge abutments, with faster execution time than with other alternatives. Steel sheet piles can be installed in advance of other works, and there is no excavation for foundations required. And finally, steel sheet piles have immediate load-bearing capacity as they are being filled. At the bridge end, many times there is the need for vertical walls or retaining walls. Compared to cast-in-place walls and their extensive foundations, modular precast wall systems such as modular reinforced soil retaining and geosynthetic reinforced soil wall systems can be assembled and connected on-site to create modular precast walls. The two common forms of this include mechanically stabilized earth wall systems and modular block systems. The wall foundations are smaller because the wall is tied back to the soil for the reinforced systems. And installation of this type of wall can progress rapidly because the system is built while the soil is being backfilled behind the wall. Next, we will look at buried steel bridges, which is kind of a combination of sub and superstructure. There are two kinds, corrugated steel pipe, which many call culverts, and corrugated steel plate, which is an arch-type structure with foundations at each end. For this first case study, this corrugated steel plate buried steel bridge was built on Route 2B in St. Johnsbury, Vermont. The bridge was fabricated and designed by Big R Bridge out of Greeley, Colorado, and built by J.P. Sicard. The bridge is located on a steep, narrow site on a curve with residents living nearby. With the poor soils at the site, the designer needed a system that could accommodate significant differential settlements between the two supports. Limiting the number of days the trail would be closed and constructing the bridge before the peak summer and fall seasons was a priority. The contractor had a minimum 50-day closure of the roadway, but earned a monetary incentive when it was reopened after only 45 days. The ABC project used precast concrete foundation blocks and precast wall panels to significantly shorten the construction time with no concrete curing times. The corrugated structural plate is shipped to the site and bolted together to make the arches. Light equipment can be used to lift these arches in place, and they connect together across the width for stabilization. The bridge arch is covered with soil and the roadway built. This video shows how a single arch is lifted and placed on the foundations. I have sped up the video 4 times, since it is such a simple and, I will admit, fairly boring process. But it does demonstrate how light equipment can be used to erect the superstructure part of the buried steel bridge. A buried steel bridge is lighter weight, flexible, and able to handle anticipated settlement better than conventional bridges. With the lightweight structure, they were able to use precast footings. Because of the arch, shorter spans are required to achieve the vertical clearance requirements. And there is a continuous road surface with no bridge deck or joints to maintain. Plus, in my opinion, this is just a beautiful bridge. Here's an example where the choice of material met a need in the effort to replace a bridge in an emergency using accelerated bridge construction. Rain flooding took out several bridges in Buffalo County, Wisconsin, including the Sheps Valley Bridge, which connects a state highway to about 20 homes and production farms. The emergency replacement was in the winter months, so concrete curing would be problematic. Wheeler Bridge from Des Moines, Iowa, designed a steel rolled beam bridge with timber decking and steel and timber substructure so that there was no need for concrete on the bridge. The bridge was built by J.F. Brennan. The substructure was built with driven steel piles and a treated timber abutment. The superstructure was rolled beams with simple cross-frame diaphragms. A timber deck with an asphalt overlay was installed. And finally, a crash-tested railing system was installed. No concrete was required. The project delivery was nearly 3 times faster than the DOT method of design bid build. The use of steel beams was a key component of the expedited project delivery. All components could be erected during an emergency during the cold winter months because no reinforced concrete was required. Staying with the idea of rolled beam bridges, modular rolled beam structures are a common technique used for accelerated bridge construction. 2 beam elements are fabricated in the controlled conditions of a shop, shipped to the site, and placed on the abutments. One option is to precast a deck to the modules, ship the units and place the abutments, and use an ultra-high performance concrete for a closure pour between the modules. This is a rolled beam modular bridge built as a bridge replacement project for State Road 30 near Pittsburgh, Pennsylvania. The contractor was Brayman Construction out of Saxonburg, Pennsylvania, and the modular units were fabricated by Quality Bridge and Fab out of West Middlesex, Pennsylvania. The precast deck was cast onto the modular units by Brayman Precast. The project included demolition of the old structure, replacing the abutment stems and approach slabs, and constructing the superstructure with the modular units. The single span structure was replaced using accelerated bridge construction methods. Working 12-hour shifts, the old structure was removed and the new one installed in 57 hours. The road was closed Friday after rush hour and open Monday morning before rush hour. The beam size is W30 by 99. They were 54 foot long with simple channel cross-frame diaphragms. The modular pairs were assembled, the deck was cast, and the modules were shipped to the site and set. Ultra-high performance concrete was used for the closure pour between the modules. This video shows a great accelerated bridge construction project. They come in on Friday night and they start unstitching that bridge and tearing it down. Cleaning up the mess, the next morning they start building up the stems to that abutment wall. They had to deal with some weather issues. That night, they're ready to start putting that first module in place, while on the right side, they're working on those approach slabs. And those pieces just go in side by side. It'd be nicer if they had removed that hydraulic crane so we could see a little better. Now they're going to start working on the approach to the left side. And now they're starting to do the closure pours, and they're finishing up, letting partial lanes on there and finishing it up. Quite an impressive project. With minimal disruption to traffic, the old bridge was removed and the new bridge was ready for traffic. Did I mention it only took 57 hours? That is quite the project. For another type of modular system, the Short Span Steel Bridge Alliance developed a new concept called a press brake tub girder for an economical steel bridge design that meets the needs for accelerated bridge construction. The idea of tub girders has been around for a long time, but they are usually for larger structures with tub flanges and webs that are cut from plate and welded together. The general idea of the press brake tub is that a standard width plate is bent into a tub shape, maximizing its performance with no waste of steel and no welding. The tub can be pre-topped with a concrete deck, and the modules shipped to the site and assembled with ultra-high performance concrete closure pours. Several have been built across the country. However, the example we're going to look at first here is a special case of the press brake tub girder. This press brake tub bridge was a replacement for an existing bridge in Muskingum County, Ohio. This bridge is special because the tubs are composite with a sandwich plate system deck that is about 2 inches thick. The result is a low-profile bridge that did not require extensive approach work, or even though they were increasing the hydraulic opening for the crossing. The tubs were bent in a press brake by Mako out of Ellsworth, Kansas, and fabricated by U.S. Bridge out of Canton, Ohio, with the sandwich plate from SPS North America out of Banks, Oregon. The steel was galvanized and metallized for long performance by AZZ Galvanizing. So the girders are bent in a press brake, galvanized. The sandwich plate is only about 2 inches thick, made from steel plates sandwiching a polyurethane elastomer core that is attached to the girders, and then the girders are loaded up and shipped to the site. This video shows just how easy the bridge was to install on the abutments. Okay, I get the background noise to that video that you don't hear because the AGA system doesn't allow that. In a little bit, we're going to see a video where it does. We do need the sound, and we are going to switch to a YouTube video. But the bridge was erected from one side due to the light weight of the modules in 20 minutes. There was excellent match fit and dimensional accuracy due to the shop fabrication and the sandwich plate quality. There was no concrete, so no curing time, and the bridge had immediate load carrying capacity. And the locals appreciated the 30-day road closure with the ABC modular bridge. So that was a special one with the SPS decking. Here are two other press brake tub girder bridges. The left bridge from Mercer County, Pennsylvania, shows a skewed bridge with precast concrete panels placed on top of the erected tubs with openings in the deck for grouting the tub studs to make the bridge composite. The right bridge from Monroe County, Michigan, had precast decks on individual tubs fabricated in the shop and shipped to the site. The modular units were placed and closure pores connecting the units completed the substructure or the superstructure. These two bridges were designed by Construct, which is affiliated with Valmont. And we're going to take a closer look at one of these bridges in the April 14th webinar on manufacturer bridge systems. So the previous case study showed bridge types and modular fabrication techniques that provide accelerated bridge construction. The lateral slide bridge construction technique is where the planning and the construction method results in ABC. Here, the bridge is built on temporary supports, usually by traditional construction methods, next to the final bridge location and pushed into the final position. The off-site construction improves safety and traffic disruption is minimized to when the old bridge is removed and the new bridge is simply slid into place. This case study, the Interstate 44 bridge over the Gasconade River in Missouri, is an excellent example of the lateral slide construction technique. The bridge was fabricated by DeLong's out of Jefferson City, Missouri, and installed by Emery Sapp & Sons. The composite steel plate girder bridge is 670 foot long with 6 spans, a very large bridge when you think of simply pushing it into place from the side. So here's the one where we need to hear the audio. So I am bringing in the YouTube.
I remember the day we pulled up and looked at the job, I turned around and I asked Rusty and Chip, I said, "You guys up for a challenge?" I said, "The way to do this project is build your existing bridge beside it, roll it in, and mitigate this whole river and all the flooding we have here." It overwhelms you at first because it was a bridge of considerable length and a bridge of considerable height, and the tributaries down there you're working over. All that added together would give you reason to pause.
We've built a lot of bridges, so it wasn't so much erecting the bridge, but getting it from point A to point B. And being it's never been done in Missouri before, and I don't know how many times it's actually been done, period, but supposedly this was the largest bridge that's ever been slid.
We had Teflon bearing pads, a stainless steel plate that went from the temporary bent all the way across to the permanent bent. We used soap as a lubricant to actually allow the Teflon to slide on top of the stainless steel. And then on each pier we had a hydraulic ram. There were 7 locations. Each one was synchronized to a central unit that actually controlled the hydraulics. It would push the bridge about 2 foot, I think, and then the ram would actually pull itself forward, and then it would fall into 2 locking keys and then push against it, and it would continue that process until it got it into its final position 40 feet away. At the end of the day, when we actually got it in final position, we had our surveyors out on the project to check at each bent location at centerline. We had already previously marked where centerline should be. They went out and verified, and when we completed the push, the most we were off was 1/4 of an inch, and the least we were was as close as a thickness of a hair.
Once we moved the bridge over, and we knew we still had to tie in the roadway, but once that bridge slid over, I mean, the feeling It was pretty special.
All the risks that was associated with the project actually came true. We were able to show that. We eliminated the risk and still completed the project on time with several delays involved in the process, and still were able to hit the target date that
Wow. That is quite the project there. So there was a 20-day bridge closure compared to an over 2-month closure required for traditional construction methods. The 2,050-ton bridge slide took 10 hours. That is quite a feat of engineering. Now, truss bridges have always been a favorite of engineers and the public. Fabricators and bridge manufacturing firms can prefabricate truss modules for shipment to the site where they are erected to complete the truss. Building the truss in the shop has the benefit of quality and fit and finish. Also, the shop's ability to apply steel protection systems such as galvanizing, metallizing, or painting is higher quality and more economical than for when it is applied in the field. For this case study, in Blaine County, Montana, there is a truss that lasted 110 years. Remarkable in itself, that finally needed replacing. That is shown on the left here in the slide. Now that's already when the deck has been taken off and some of the pieces, but that shows the old truss. A new truss structure was chosen to avoid elevating the approach road grade and keep the structure above the 100-year flood elevation. The fabricator was Contech Engineering Solutions out of Westchester, Ohio, and the contractor was Kopp Construction. The design, fabrication, and construction was recognized with a Best Bridge Award by the Montana Contractors Association. Demolition of the old truss and construction of the new two-span truss with a concrete deck used approximately 7 employees. Here we see them starting to do the substructure work. The steel truss bridge was delivered in large segments that were bolted together and lifted into place to speed erection and installation. A 300-ton crane lifted the 2 main 148-foot trusses, and a contractor-owned 110-ton crane lifted the 2 79-foot approach trusses. This video shows the demolition of the old truss and the construction of the new truss. The old truss is gone. They're starting to build the foundations and the substructures for the new bridge. There, they're lifting in the main trusses with the 300-ton crane, putting on the deck panels, putting in the approach truss, completing the deck panels, and it is ready for the deck placement. I think this video also shows some pretty high quality and cool drone footage where they could match the picture so it didn't get distorted and some weren't closer and some were farther away. Came out to be a really nice video. Now, due to flooding, the contractor only had 8 days available to build the structure before the concrete deck placement people were going to show up. But they made it work. The trusses were lifted into place, the floor system was built, and the deck panels were installed for the concrete deck formwork. Here is a large, traditional truss bridge erected with accelerated bridge construction that will last even longer than that original bridge. Our final case study bridge will be a bridge built with accelerated bridge construction using prefabricated elements in an environmentally sensitive area where conventional construction would not work. And I know I'm going to mispronounce these names since I don't speak Hawaiian, but the Keahua Arboretum in the Keahua State Forest in Kauai, Hawaii, I got through that at least, is home to native plants and vegetation enjoyed by locals and tourists for picnicking, swimming, hiking, biking, horseback riding. They needed a bridge to replace the troublesome low water crossing that would stop visitors from being able to cross during rain events, and a bridge that fit into the natural environment. The build site was very tight, and the owner required little disturbance in the construction. The solution was that Acro Bridge from Parsippany, New Jersey, designs and builds prefabricated individual truss elements to assemble bridge trusses in various forms. The new bridge was a 110-foot long single lane bridge with a protected sidewalk on one side. The bridge was built by Macon. The prefabricated truss elements are packed in containers and shipped to the site. For this bridge, there was a three-man crew that put the bridge together with only hand tools. Because of the lightweight trusses, they only needed temporary falsework in the creek to place the bridge on the abutments. The roadway decking was lightweight prefabricated units that were installed on the floor system. No heavy construction equipment was necessary. When you think about it, the reason many of us became engineers is because of our Tinker Toys, and Acro has continued that passion to produce prefabricated bridge element bridges to meet those bridge needs. The bridge in a garden fits the needs and the environment for the state park, and the prefabricated elements met the shipping, staging, assemblage, and erection requirements for this remote region with the tight build area. And with this beautiful bridge setting, we will summarize today's presentation. When this webinar started, I stated that bridge designers, fabricators, erectors, and contractors are innovators in delivering bridge projects to owners. We have seen a few accelerated bridge construction case study examples of how planning, design, choice of materials, and construction methods have been used to greatly reduce construction time, improve work zone safety, and decrease the inconvenience to traveling public. So this concludes the Steel Bridge Accelerated Construction Applications webinar. We looked at several applications in ABC. Some of the case studies we discussed are typical design bid build projects, or design build projects that use modular units and construction techniques to greatly decrease the construction time and the disruption to the public. Others were from bridge manufacturing firms that will design and deliver a bridge that can be installed quickly for accelerated bridge construction. ABC has become an important part of the bridge industry in that it reduces on-site construction time and inconvenience to the public. In the April 14th webinar, we will look at a showcase of bridge case studies that these manufacturing firms can design, build, and deliver to the bridge site. Bridge manufacturing firms use experience and economies of scale to produce high-quality, beautiful, functional, and economical bridges for owners across the country. Many of the examples we will look at on April 14th would certainly also qualify as accelerated bridge construction projects, as we will see. So I thank you for attending this first webinar of the 7-part series. If you would like more information about the Short Span Steel Bridge Alliance or on the topics in the series, you are encouraged to visit shortspansteelbridges.org, the website, or to contact the Alliance directly either through Twitter, Facebook, or just the contact information. So I will conclude by saying have a wonderful week and stay safe.